Okay. So again, thank you very much for joining the stream. So today I'm going to talk about resource and requests in Kubernetes, and we're going to have a special guest with us today to dig a little bit deeper in what kind of sort of problems and scenarios you will need to face when managing resources in Kubernetes. So let me just show you. So let's start by saying who I am. So my name is Daniele. People call me Daniele, Dan. Any name works, and they also make fun of me. They call me D5E, which is a nice way, I guess, to recall the Kubernetes. It's a shorter version for the Kubernetes name. And I was lucky enough to speak at KubeCon 3 times, and I was one of the first 500 people to obtain a CKA certification back in 2017, when the exam was 3 hours. Things have changed a lot since then. We still have a CKA, slightly different, but I'm quite proud of what I achieved at the time. What I do, I generally run workshops, so I teach people how to use Kubernetes. I focus on core Kubernetes and how it works. And our next workshop is actually online next week, so I'm going to share the links if you want to join. I'm part of a company called Learn Kubernetes. You probably, if you heard of Learn Kubernetes, you probably know that we maintain a number of brands where we share knowledge and news and articles, tutorials, and events to help you level up on your Kubernetes knowledge. So all of those accounts, they tend to focus on sharing material that you will find useful to level up your Kubernetes knowledge. And today I'm going to talk about resource and requests, and I'm going to focus on a particular area of resource and requests, which is basically getting them right. And I'm going to share part of my journey on how I thought I could do it just by guessing it right, and then slowly how my perception of how this should be set has shifted as I learn more on how they work. And I'm going to have Andrew helping me. He's going to show a real case scenario, real case studies from real companies, real sort of deployments. And you will see how what we explained today is going to translate to real deployments. So it's going to be quite interesting exploration. Cool. So let me just start from the beginning, set the scene, and try to explore what we're going to cover today. So first of all, what we have is generally is a Kubernetes cluster. A Kubernetes cluster is a collection of servers where we have one of these servers being the control plane and the others are worker nodes. And what we do is we generally join them together into a cluster, and this cluster generally looks like a single unit. And then we deploy workloads in this single unit by just doing kubectl apply. And this will basically create these pods, these containers in cluster. Now, what happens on, behind the scenes is that Kubernetes needs to place these workloads somewhere in the infrastructure. So we'll need to find ways to place the container that you created. Now, when we create a workload or a pod, generally what happens is the request is sent to the control plane, and then there are several components in the control plane that work in concert to create this pod. So let's imagine that you want to create a deployment with, let's say, 2 or 3 replicas. Then this deployment, first of all, passes through the API server, where we have authentication, authorization, and a few other things, and then it's eventually stored in etcd. When it's stored in etcd, then the controller manager will basically be notified of the change, and then inside the controller manager, we have several controllers, and 2 of those controllers will be basically activated. So the replica set controller and the deployment controller will basically create those pods. And the pods will be stored again inside etcd. And inside etcd, they will basically be stored as pending, so a pending status. And at the same time, those pods will be added to the scheduler queue. And the scheduler will basically look at those 2 pods one at a time and basically figure out where the pods should land inside your infrastructure. Now, the scheduler it's quite complex, it's quite interesting piece of technology, but generally the way you should think about it is that the scheduler needs to identify where these pods are placed inside the infrastructure, so it will need to go through 2 phases. The first phase is basically filtering out nodes that are not applicable And then of the one that are applicable, then we will need to find the best one, and that's usually called the scoring phase. Now, part of the scoring phase and also the filtering phase, we have requests. We have the request. So generally, what happens is when you deploy a pod, then the scheduler needs to identify where in the infrastructure this pod can be deployed. And one of the things that it's going to look at is how big is this pod, right? But the issue is that because the application is not deployed yet, we don't know how much memory and CPU is using, right? There is no way for the Kubernetes scheduler to have this kind of information. So it doesn't know if the pod should be deployed on the left or the right. So to solve this, generally what we do is we give the scheduler some hints. And these hints, they come in the form of requests. So when we say request, what we basically say, okay, these are basically the resources needed, the resources currently to run this application. And then at this point in time, the scheduler understands, oh, okay, this is the size of my pod. Then I know if it fits or if it doesn't fit inside my infrastructure. And if you were to look inside a YAML, that's generally what we do when we define resources. We basically have like a small section where we basically say, okay, this is how much CPU I want, or this is how much memory I want. On top of that, of course, we've got something else called limits, which is basically the maximum moments. But most of the time, all of the time, the scheduler will just look at requests when it comes to placing these pods inside the infrastructure. Now, how are these requests and limits related? So generally, when you define requests, you're basically defining the minimum guaranteed resources that a container is going to utilize. So in this particular case, I selected, a quarter of a CPU, 5 to 12 megabytes of memory. Those are my requests. And then what else I can do, I can set basically limits. And basically limits what are the maximum amounts of CPU and memory that container is allowed to use. Now, everything in between is something that the application can use. And this is a curse and I was going to say, this is a curse and a blessing. And the reality is that not just the container will use all memory and CPU between the request and the limit, but it can also use less of what we defined in the request itself. And this is perhaps where things start to get a little bit more complex. Now, there are a few things that we generally recommend when it comes to requests and limits. And the first things that we always recommend is to always set the memory limit. And a memory limit is basically the maximum amount of memory that a container is allowed to use. And then if it uses more of that memory, then that process will be killed. Why do we need this sort of limit, the memory limit? The idea is that if there is something like a memory leak, we don't want this container to use all the available memory. We want to stop it somehow, because that could affect not just that container, but all of the rest of the node, the applications as well as the node. So generally, not a good idea. And let me show you what happens if you don't set a memory limit. Then this pod will start growing. And as the pod grows in memory, then it's going to hit something that we call the eviction threshold limit. And the eviction threshold is basically a threshold saying that when it's crossed, the kubelet will say, okay, I don't have enough space in this node, so I'm going to try and evict some of the pods to make space. So as the memory grows, then the kubelet will start to evict pods, but there will be more memory now. And then that pod will start to use that freely available memory. And then the kubelet will realize that we are, again, over the eviction threshold because the memory leak is growing. And then the same will happen. We'll just evict more pods. And then the pod with the memory leak will just go and get all these extra memory that's just been freed. And then so on and so forth until basically this pod will basically eat all of the available memory and evict all of the available pods on that node. And at the end, what will happen? This pod will still get too big and it will be evicted itself. So it's basically just like a very carefully crafted time bomb when it comes to memory limit. CPU limits, so we talked about memory limits. CPU limits are generally a little bit more complicated, and because memory and CPU are quite different. So generally, when we talked about CPU, the CPU is allocated in quotas. So every, 0.1 seconds, you're allocated a quarter of CPU. In this particular case, I've got 1 CPU. And what happens is you're allowed to use that quota, but if you don't use it, then it's basically lost. And your application can use that quota anytime during the interval to do processing, any type of processing. But what happens is if it uses more CPU than what is allocated, then there isn't enough. And then what we need to do is we need to basically wait for the next period to actually execute that unit of work, right? Because we've gone over the limit and we cannot use anything more than that, so we need to wait for CPU time in the next quarter. Now, the problem with this is that, let's say you have an application like a JVM. This is quite common to see on, I don't know why, I don't know why in particular with the JVM, but this is, the experience I've got is that most of the time when you have like a Spring Boot application, you expose an API and you're very tight on the CPU limit, then what will happen, you see the Spring Boot coming up very, very slowly and you don't understand why. But another example is, you have an API and then what happens is the CPU limit is so low, then it will do some work, then it will get stopped because it doesn't have enough CPU to actually complete the processing of the API, going back to the database and, deserializing the values and then going back to the user. It doesn't have time to do all of this. And then what will happen is it will basically be paused and then we'll need to go to the next quarter, to the next period, to do a little bit more processing and so on and so forth. But if the limit is so tight, so small, then you will need to do this almost every period, right? Which is basically going to extend how long it takes to return this response from the API. This is why generally CPU limits are a little bit problematic because it's very hard to understand how to use all of this quota and when this quota is going to be used in full and is going to be moved to the next period. But if you thought that this was complicated, wait until you realize what happens when you use threads. Because when you use threads, what happens is you basically have the same limit, but you're just sharing it with all the threads inside the application. That basically means that I've got 8 threads here, and each block is like a 0.1 CPU, so like 100 millicores. And what happens is if all of these cores wants to use 200 millicores, then 8 of them will need to be stopped and will need to process their unit of work in the next period, right? But what happens if I have got a thread which is just monopolizing all of the CPU? Then this is even worse because all of the other threads will basically be blocked. We'll need to wait for the next period and to do any sort of processing. And what if the next time is, not the first thread, but the third? And, and all of these threads are basically different, requests or responses coming from the users. So you will see, the requests coming in and going fine, other requests coming in and being super slow, and it will be very inconsistent. That's why CPU limits are very unintuitive, and it's generally best to not set them than to actually set them and end up in this situation, which is very hard to debug. So what we do generally is we always set memory limits. We always set memory requests. So we basically say, what is the minimum amount of memory that this process is going to have? We always set the CPU requests. So we basically say how much memory, what is the minimum amount of CPU that I need to assign to this container. We always set the memory limits, and most of the time we say we don't set the CPU limits. And why is that? It's because if there is spare capacity, if there is spare CPU, then this spare CPU can be used by the processes. And then, you might argue, but isn't that going to eat all the CPU on the node? No, because requests are guaranteed. So if you say, I've got 1 CPU requests, then that one CPU cannot be taken away from that process. So this is generally safe to not set CPU limits. But the real challenge right now is, okay, I know what to do with memory limits, I know what to do with CPU limits, but how do I get the right requests and the right requests for CPU and memory? So we said that basically what we have is actual memory and CPU can fluctuate between requests and limit, and can be also be lower. So if we were to visualize this, and then we draw some square boxes for the requests, and what we say is requests are guaranteed, so no one can take away from me the CPU or memory that I define. But if the actual usage is less than what I requested, and no one can take away from me the requested resources, then I'm basically wasting all of these extra memory and CPU, right? And this is a problem, because if I define a request very high and my actually memory usage is low, then I'm basically wasting all of that resources that are in between the two lines. Now, this is slow request, but let's have a look at if you set the requests. So if you set the request too high, but let's have a look at the opposite. So if you set the request too low, what is going to happen? So in this particular case, what I have is a request like before. So those are the guaranteed CPU and memory assigned to a container. And then I've got something else called the limit. So this is basically, the maximum amount of memory and CPU that I can use. Now, if my actual usage is always more than the request, then I'm fluctuating between the request and the limit. Now, this is generally good. The issue that I've got here is basically I'm using more requests than actually I define, and the request that I define is guaranteed, but all of the area above the request is not guaranteed. It's something that I need to basically compete with other processes to have, and it might not be there for me. So it is a risky situation. And then the other risky situation is that, okay, if I define the request too low, then the problem I've got, I need to compete with other processes. So perhaps all of my application will be a little bit slow sometimes because they need to compete on CPU, or they need to compete on memory. So generally not good. But on the other side, if I'm really a bit too conservative with requests, and I say, okay, I'm going to set the request very, very high, then because these requests are guaranteed, then basically I'm not using some of the resources, and I'm basically just wasting this compute, this CPU, this memory. So which one should I go for? Should I go for a terrible DX, or should I pay more? Okay. Well, it turns out that it's actually even more complex than that, because it's not just that your application will be up all the time or down all the time. Actually, your application will fluctuate between too much, over the request or under the request. And it's not clear that it's going to be like this either. It could be like very low under the request and very high, so asymmetric, or it could be very narrow. But very narrow is actually where we want to be, because if you have your applications to be, if your profile is very narrow, you basically say, okay, I'm very, very close to the request. Yes, I can make some errors, but overall, I'm close to the request I define. So this is ideal. But how do I get to ideal, right? How do I set my request limits knowing that I don't want to have great variations? So it turns out that what I could do is, if I've got long variation and if I don't know what my request and limits are, what I could do is I could instead of just setting one request and limits, I could divide my time into periods, right? And say, okay, I'm gonna evaluate period 1, period 2, period 3, and so on and so forth. And for each period, I can basically define the max request and the min request. And then for each, if you were to imagine to set the request for each period, then the request for each period would be the average of the max and the min, and it would be a very, very narrow interval. So basically, the new intervals are like very, very narrow, and I'm basically solving the problem of going from a huge variation to a very narrow and small variation, but just doing this trick of dividing everything into interval. Now, I'm doing this, but I'm basically cheating a bit, because I know already what is the min and max. I'm just looking back in the past. But what I need to do now is take the next step, which is basically saying, okay, I've got this max request and min request in this period, but I need to guess what is going to be the next period. Is it going to be high, low, mid, or low? And it's going to be like a large interval or a small interval. If I can guess this correctly, then I can set the very precise value for requests and limits. And if I can do this for all the intervals, then I can be very precise and I can save money and not use too many resources in my cluster. Now, it turns out that this problem is quite complex because you need to do it all the time, right? If you consider an interval quite short, like even just like an hour, you will need to basically identify these values and then find what is the correct value for request limits and then set them. And you need to do this for every container, every pod, every deployment in your cluster, which will be a lot of work. So how can we automate that? It turns out that the Vertical Pod Autoscaler does this. It's basically a component that will analyze your previous usage, and then it will basically readjust it, right? It will basically readjust requests and limits based on the historical data. And this will basically function in a similar way that we described. So we'll just look at this period and then just adjust them. Now, but this is basically the only tooling, open source tooling that we have. Then there is like another set of tooling, which is not free, which is mainly paid products. And then what they do is they don't just do a regression on the values that are extracted from Prometheus, for example, but also apply machine learning on guessing what is going to be the next interval and how to adjust this value. And these are basically the tooling like StormForge, Perfscale, Cubex, and Densify, Tubenomics, Scale Up, Cast.ai. I mean, there are like a lot of tooling in this space. And then the thing I want to take you away from this, and then Andrew is gonna show you how this stuff works, is that most of these applications, most of these vendors are consolidating. So what we're saying is basically we're seeing some of these companies being bought out or merging with other companies. I think this is basically signaling that there is a lot of interest and movement in the space. So, which is good because I think this is a real problem, and we're trying to find a way to solve it. Now, so I showed you how this stuff works and how to basically guess the requested limits by using some sort of time slicing and sort of guessing the next block and figuring out the min max for requested limits. Show you some tooling, but I think the best way to actually show you this is to introduce you to Andrew. So Andrew is the CTO and co-founder of Densify, and they've got a product called Cubex, which is basically it's a proprietary product which basically analyzes this pattern like we described, and then finds the correct value for requests and limits as well on those particular workloads. So Andrew, I'm gonna find a way to show you. Yes. It does work. Andrew, thank you very much for joining the stream. Thank you very much. And I'm gonna hide myself, and then hopefully, yes, we're gonna see all of these real stuff from yourself.
All right.
Let me know when you're ready.
And can you hear me okay?
Yes, I can.
So give me a second. I'll just share my screen. Let me make sure I'm sharing the right one here. And while I'm doing that, thanks, Danielle. That was an excellent overview, or sorry, D5E, as I'm now going to call you from now on. Sorry, let me just see if I can share my whole screen here. It's probably the easiest way. I'm sorry, it's having a bit of an issue giving because you want to see my screen, otherwise it's going to be a lot of words with no context.
Yes.
So 1 second here.
Yeah, not a problem. I see there are a lot of people from just already asking questions. Andrew, if you want, I can start looking at some of those while you prepare.
Okay, yeah, please do. So I'm not sure what's happening. I can't seem to share my my sandbox.
Okay,
not one of the options. So.
Okay, I will look at some of the questions while I wait for you.
Okay, I actually have it up now.
Okay.
And Danielle, just for time wise, how long? I think we're nearing the bottom.
I think we probably have like 5-8 minutes for sure. So I think that will be enough to show how this stuff works for real. Okay. I'm just going to disappear for a second, so there is plenty of space to see what you have to present.
Be very quick, and I think what you presented was spot on. That's exactly the problems we see, and we think they're so important that we created a product to solve them, and that's what you're looking at on the screen. And I will just give a very kind of quick overview. And I'll contextualize, again, you hit all the main points. If things are too big, they're expensive. If they're too small, they're risky. If your limits are too low, you get killed. That's exactly what we analyze, and we do that on scale, and then we automate the fixing of that, which is very important because it's one thing to have understand what one container is doing and it's between its request and limit and all that's good. But if you have thousands or tens of thousands, or we have customers with hundreds of thousands of containers, that's not practical to do manually. So what I'm looking at now is kind of a front screen of a Kubernetes analysis. And I'm not going to spend long here. This is more of a FinOps oriented view. I know there's a lot of detail here, but it's basically saying you're spending a lot on the infrastructure running containers. If you fix the requests and limits, you'll be spending less than half. And there's details on how to do that. There's things that are safe to do. There's things you need to fix, like out of memory kills, before you go any further. But what we try to do is say, look, if you do these things in this order, you're going to get to that nirvana that you've been describing, where everything's running efficiently. And before you get there, the big problem we see is a lot of cost. So that's usually, if we have a booth at a trade show, we'll put, cost as a headline thing because everybody understands, this stuff gets really expensive if you don't set it up correctly. Risk is very important too, though. So Dan, what I'm going to do is I'm not going to spend long here. These are, I'm looking at an environment. It's a real environment. There's only about 2,500 containers, and these are the clusters, and these are the namespaces, and these are the pods and the containers. And we're analyzing all of it. But what I'm going to do is go to this histogram, which really tells the story. I'm going to try and go to the histogram. Let me just come back here. And this is a visualization of exactly what you were describing. So this is, we call this the 4-pack. At the top left are the CPU requests, top right are memory requests, CPU limits, and memory limits. And it's basically visualizing how wrong they are, is the simplest way to put this. And they're usually very, very wrong in every environment we analyze. Even the most savvy environment customer that we see will have these issues. And this is real data. And the way you read this is, from a CPU request perspective, out of the 2,500 or so containers, only about 500 are actually set correctly. There are a whole lot that are too low. Well, I wouldn't say a whole lot. There are a bunch that are too low, including these buckets are, these ones are 50% is they're half the size they should be, or a fifth the size they should be, or less. So this is an example of a container that you gave one CPU to and using 5 or 10, which, as you pointed out, creates risk. If I have too many of them running on a box, I have a throttling risk where the node can get saturated, which we're actually detecting here. So we're trying to roll up exactly what you described on scale. You can view this picture for any size environment. The gray is unset. You didn't give it a value. I love your advice there. Always set requests. Kube system, sometimes we see them not set, but outside kube system, you want to have a request value. So there's a bunch that don't have requests, which create risk. But the big story here is this big yellow bar. About over 1,000 containers are 5 times bigger than they need to be, or bigger than that, 5 times or higher. And this is what creates that cost problem. So right away we see this. And so from a FinOps perspective, the yellow bar is very much of interest. This is what I'm worried about. We also see, for example, if I go to memory, it's a little more complicated. And you described this as well. I have some that are too big and some that are too small. There's a bit of a mixed bag and a bunch without any values. And this messes up the scheduler because Kubernetes doesn't know what to do with these things. You ask for a gig and you're using 5. And if you do that, you can blow up the node as you described. So yellow is cost, red and gray are risk. You can have an environment with a surplus of capacity because I have a lot of oversized things, but also some nodes that are running out of memory. And so when we see this spread, that's a problem. That means you could have out of memory risks because of node saturation. So it's exactly what you were describing. There's cost, there's risk, and then these limits. The gray bar, you described this very well. If you don't give something a memory limit, it can take over a whole node. And we've seen that happening. We've caught that. So you want to give everything a limit. And even more evil is things that have a limit that's too low. So let me drill on this one very quickly and show this, because this is the one that almost becomes the most interesting. From a cost is important, but if I have things hitting their limit, we're in here saying I actually have containers that are hitting their limits and restarting. And I'm going to go in here and just show that very quickly. These are each line item in this table is a container. And we have various views in this table. This table works kind of like Excel. It's pretty powerful. But this top row, we're saying this thing is hitting its limit, and it restarted 145 times yesterday. And this is that machine learning pattern. So we're basically doing machine learning on all the history of this thing, saying, yeah, it looks like early afternoon, it's hitting its limit and restarting quite a bit. Or if I go down a couple of rows here, here's one. This one's pretty interesting. This one is just hitting its limit nonstop every hour of the day. This is a 24-hour view of the kind of utilization profile across that this thing typically does. So this is pretty, this is pretty bad. I can drill down to the what's this thing do every day back through the last quarter or every hour, right down to the Prometheus samples. I'll just go right over to this one, where we're saying what exactly is this thing doing, on a minute by minute basis. And this is very bad. This is what you talked about as far as the risks occurring. If this thing's hitting its limit, we want to fix this, and we're recommending a higher limit. We're saying bump the limit up to a higher value based on these utilization thresholds. And if I want, I can even automate it. I can just choose that workload, or I can choose entire trees and say just fix it automatically, which is kind of the holy grail. So when we see risk, we really want to fix these things pretty quickly. And as you described, unset limits or limits that are too low are usually a very high priority. And so that's one thing we see. And then the other thing I'll do, and I only have limited time, so I can't go through all of these things. By the way, what I'm in is our sandbox environment that you can access. Anybody can access from our website. You can sign up and go in here and see exactly this. So feel free to play around with this and explore it. But the last thing I'll show is there's these risks, and then there's the cost. So if I drill down on the yellow bar, these are all the containers that are way too big. And so, for example, this one, it's an analysis container. It was given 4,000 millicores, and we're saying it only needs 1,600 millicores. It's way too big, and I can see that in these curves. So this workload typically uses about a half a CPU, give or take, most of the morning, and around noon it goes up a little higher, and it peaks around 2.5 or almost 3 CPUs and comes back down. And so the request, though, is for 4 CPUs. This is way oversized, and you don't need to request that. You don't even really need to request the peak. You could, and this is all policy driven, but we're suggesting, why don't you request just above the sustained activity as a start, and you will save over half, and this thing will still work just fine. It's still protected for the bulk of its processing. It can peak up above the request, as Daniel pointed out, like that's fine. The nodes have plenty of CPU, and we're checking all of that. So this recommendation is going to save quite a bit of money because we're chopping this thing in half. And there's actually 30 replicas of this thing. So overall, we're going to save about 70 CPUs by fixing that one. So we see this everywhere. We see these are real workloads. We see, in some customers' cases where one container is wasting 1,000 CPUs because it's so highly replicated. It's about $250,000 a year. So again, and the idea is I just want to fix this. I can click on this workload. I can go to its what we call homepage. I can see everything about it. I can share links to it. Hey, I want to send this to whoever owns this workload, and I can just say just automatically fix it, and that will just automatically adjust the requests and limits based on those utilization patterns, so everything is set correctly all the time. And when you do that, I'll just go back to the histogram here. What happens is all those yellow and gray and red bars become green, and the green bar goes high and the other ones go down, and you save a ton of money, and the other memory kills stop. So that's kind of what it looks like in real life. These are real workloads, real containers with real patterns of activity. This is a small environment, but especially when you point this at bigger workloads and bigger environments, it has a very big impact very quickly. So Danielle, I think D5E, I think I'll stop there and in the interest of time, but hopefully that made sense. And again, like I said, if you're interested in going deeper, you can click around this yourself. It's available on our website.
Yes, we're gonna share the links in the comments. I think that's a good idea. I've got plenty of questions, Andrew, and we've got some questions from the audience as well. So what I will do is I will try to share my screen and just sort of close and explain at least what I learned from all of this, and then we're gonna jump into the questions. Let me just find okay. So takeaways for me, at least, what I've learned from all of this, which is, it's been quite a journey, to be honest. Okay, so simple things like Andrew suggests as well, always set request. That's generally, a very good start. The other sort of challenge is understanding these oversubscribed versus undersubscribed. So when we set the request too low, and when we set requests too high. The other things which, I give for granted now, but it took me a while to actually crystallize in my mind was, okay, I used to think that request and limits is something that you set right the first time and it just works. But there is no there is no right when it comes to setting requests and limits, because the application can change, the traffic pattern can change, the code can change, the infrastructure can change. So there are so many things that can change at any given point in time that we can't really set a single value and pretend that value is right all the time. So my suggestion at this point in time is you need to find ways to adjust these requests and limits dynamically, as frequent, possibly as frequently as possible, but you shouldn't just select a number and stick with it. And then we also covered two types of tooling. So we had a look at open source tooling, the VPA, and Andrew presented what they do at Densify, but there are many others. So I think the takeaway from me is that tooling is probably the way to go. Tooling on the open source is quite limited, and then there is quite a lot of competition and options when it comes to paid products as well. That's my take. Now, if this is the end of the stream, we're going to stay a little bit longer just to answer a few more questions. But I just want to thank you very much for joining me. I want to thank you, Andrew, as well, for joining me today. Cool. Said that, we've got a few questions from the audience, Andrew.
Okay, let's go.
Let's go with the first one, and then I'm going to ask you a few questions as well if you've got time. Let's see what we're doing. This one, I think this one is for you, Andrew. So the question is, isn't it better to use HPA only for managing memory resources and VPA for CPU?
That's interesting. That's a really complicated question, because we see, and I just got off call this morning, deep dive into HPA in customers, and it can be very complex. So we see people scaling VPA or HPA on different parameters. CPU is kind of a default, memory sometimes, app metrics sometimes. And I don't think I would say that it's just best memory one, CPU the other. What we would do is you got to watch the one it's scaling on, and then make sure you're very careful touching that one. But the other metrics are fair game. So if you're scaling off CPU, then memory is fair game to adjust, and vice versa. But it's a very complicated thing. We're seeing environments where the HPA scaling thresholds aren't quite right, and the mins are set too high, and the maxes are too low, and it's a very complicated subject, and we're doing quite a bit of work to recommend those settings. So I wouldn't blanket say one's better for CPU, one's better for memory. What I would say is that you got to be careful vertically adjusting the one that HPA is scaling off, because it can have very strange impact. You can have it expand out of control, run out of IP addresses, all kinds of things. So you can scale on different factors, but you have to be very careful, I guess would be my only comment on that one.
Excellent. That was an interesting answer. I've got another one. I think I don't know the answer. I think I'm just going to say Andrew's going to answer this. So the next one is, so Andrew, let's say that you have workloads which have very, very, very spiky nature. Mm-hmm. Like they use CPU like at the very beginning, and then they go very, very low.
Yeah.
So one is, how do you detect those? Mm-hmm. And the other one, what kind of strategy do you have to actually model this kind of workloads?
So, and we do see that, like a startup spike would be a very common example of that. And we have a lot of very deep policy level controls for statistical, like removing those ones, or 99th percentile. The curves I pulled up have by quartile by hour, so they model the hourly patterns, but that can also be filtered based on criteria to say we don't want it size to that spike. So we see that quite a bit. Even in general, if it's not a startup spike, it's a peak. You don't want to size to the peak, because you'll strand a ton of capacity. Like unless it's an absolutely critical workload, a guaranteed QoS, for example, is a case where you're sizing it to the max. And for memory, that makes sense on critical workloads. We see people doing that on CPU sometimes. It doesn't make as much sense, because sizing to the peak CPU will just leave a lot of CPUs stranded. So the strategy we promote is that don't size it to the peak, but size it to something more the sustained activity, but watch the nodes. And I didn't have time to go down to the node level and show you, but if the nodes are nowhere near saturated, you'll be fine, because there's plenty of node capacity to burst into. If your nodes are too busy, then you can't burst anymore. Then you have to be careful. Hopefully that makes sense. But leaving, sizing well below the CPU peak, for example, is perfectly fine if the nodes are not out of CPU, which is usually the case. Usually there's a lot of CPU available on the nodes. Yeah.
And then, sort of a question for myself now. Now we're getting more into this sort of topic. Is that so? So we talked about request and limits, and this spiky discussion also covers some of the things I want to probe. And do you see more resources wasted on the CPU or memory side? Which one is more expensive? Which one is more easy to get wrong?
Well, the CPU by far, and I think you saw that in the visual I showed, that the yellow bar on the CPU is high in every environment we see. It's just wildly oversized. It's the app teams that are deploying, I think it's very hard for them to figure out what to ask for. Either they don't know what their app's going to do, or they know what it does and they ask for something that protects too much of their processing, and it makes the system very inefficient. So CPU by far. Memory, we see a whole mixed bag of things. It's usually too much memory deployed, but like I remember I showed the histogram that had red and yellow. It's a mess. So usually there's a net surplus of memory, but not as big as CPU. But some nodes are out of memory and some nodes are using very little memory because the scheduler doesn't know what to do with all these inputs. So we've seen cases where the amount of memory deployed is exactly correct. It's just all wrong what it's allocated to.
Okay.
So generally we see a surplus of both, but the CPU surplus is much bigger.
So going back to the questions of spiky workloads, so I guess spiky memory is easier than spiky CPU.
Spiky memory, you have to handle the spikes because it's not allowed. You will get killed. Like so memory, when we analyze it, you got to meet the memory requirements of you can't have a shortfall of memory or things get killed. CPU, that you get throttled, so it's not so bad, but. So
Okay,
the policy for
challenge.
sizing memory, you want to make sure you get the memory you're asking for, otherwise very bad things happen. So it's a bit different between the two. Guaranteed QoS on memory makes sense. Guaranteed QoS on CPU is usually wildly expensive and unnecessary from what we've seen.
So you have two complete. So if you have spiky workloads, there is no such a thing as a spiky workload. I think there is a spiky memory and a spiky CPU workload.
Yeah.
And okay. That
spiky memory is more rare. Like you would see that at the pod level if there's a container running sporadically and going away again. But generally, memory curves tend to be a little flatter than CPU curves. So it's a bit of a different profile.
Okay. That was an interesting one. Okay. I think that we cover. I think we also covered the other questions. So I think there is someone else also sharing some thoughts on a production deployment, and they say that they see deployment failing due to insufficient CPU, even if it worked perfectly in the test environment. And they found out that the issue was the node had already 90% of his CPU requested, which prevented new pods from being scheduled.
Yep.
And they solved this by adjusting the requested limit, but it highlighted the importance of continuously monitoring and setting those properly.
Mm-hmm.
And I think this is exactly the challenge that most people face with requested limits. Now, Andrew, I know you'll only be biased, having Densify as your product, but some people from the audience might say, okay, I want to stick to open source tools. I understand that maybe I need to adjust things. What is the first step to sort of get into solving this problem? What would I do? What is your advice when it comes to tackling the problem? First step, slowly moving to the right direction.
So, I mean, that's a complicated question because I guess there's several parts of it. I mean, you can stare at a Grafana screen and if enough patience, figure out some of these things, although it's very difficult, especially for replicated workloads. So we see people that kind of get somewhere on a handful of workloads, but once you get in scale, that's not practical. Now, you had mentioned VPA. That's available. We don't find that has good adoption because it doesn't have good recommendations. It doesn't look at very much data. So it's interesting to learn the concept of what you're talking about, but in practice, it won't see beyond last week. So if you have something that gets busy at the end of the quarter and it hits its limit, well, it doesn't even adjust limits, so it has other limitations. So I mean, VPA conceptually is there, but we find it's not effective in practice in working environments. Now, interestingly, you have the instance calculator, which is a great starting point. That's more of we focus on the steady state kind of day two operation, watching everything and adjusting it. And your instance calculator is great for kind of day zero let's figure out what to do. So I mean, I think that's probably one of the best starting points because it's available. I believe it's open source, and it's a good starting point to understand this stuff, right?
But yes, you can use the calculator. I'm going to share the link in the comments. But the other thing is I was thinking is, if I don't have something like the VPA, what am I supposed to do? Just open a spreadsheet, keep track of the requests, and just update them manually? Is that
I think
the first step?
that might be the only option people have because there's not really any other way to do it. You need a way to figure out what they should be set to, which is in itself very, very hard, obviously. So presumably you're going to look at some data or Grafana, and then, yeah, you need to kind of come up with the values manually. There's not really anything in the ecosystem that is going to do other than the tools like ours that's going to adjust this. So it's a bit of a it's obviously a gap in the ecosystem.
Okay, that's that's interesting.
Now, what are your thoughts on that, Dan? What would you're the learn KS?
I don't. To be honest, I don't know. I think, like you say, I think there is a gap in the tooling in the open source space. And the other things I see, a lot of proprietary product like yourself, for example, and there is nothing in between, right? And I'm wondering why there is a gap. Why is it that someone thinking of this is say, okay, I'm going to build a company out of it? Is it because there is no interest? I don't know, because the interest is there. We see companies, pushing for these kind of products, but I struggle to understand why there is no open source tooling in this space. And even the VPA, I agree with you, the VPA is very limited. So there are several areas which are not advisable where you shouldn't be using the VPA. So there is only actually a narrow set of cases where you should be using the VPA. And even the VPA itself, there are some constraints. So I'm just, from my side, I don't know. I think maybe the spreadsheet is a way, but I would basically need to build my own automation. And building my own automation will basically need components such as how do I figure out the request and limits to begin with, which I don't know, I will need to figure out. And maybe I can use Prometheus for that, but is scraping quick enough? I don't know. I will need to pull all of this data, try to make sense of it, and then try a way to push it back.
My theory on that,
thinking.
And my theory on that is it's quite a hard problem to solve. I mean, we obviously do a lot of a big team of engineers solving this, and I think part of it is because, as you mentioned, there's many facets to it. You have to get the data, you have to store it in a database somewhere. Not Prometheus. It needs to be a bigger time series database. Probably commercial. Like these are all the machine learning on to understand it to come up with those answers. These are not simple things. So I think even something like VPA that operates very, very simply is actually fairly it kind of pushing the boundaries of complexity. So I just feel like it's an area where I think the complexity means that it's not easy to solve. I guess the simple way I'm saying. And so it requires kind of a commercial, in our view, like a properly engineered solution that looks at all the aspects and the policies and all these things. It's really hard to write one of those yourself, obviously. And so that's it is a very clear gap. There's an analogy I come up with. I gave a webcast one time where it's almost like my laptop. Like I sit on my laptop all the time. I give PowerPoint. I use Excel. All these things. In Kubernetes, I have to give each of those millicores and megabytes. Like that's what it forces you to do, down to that level of granularity. So if you said to me, how many millicores would you give PowerPoint? Like I don't know. I use it all day, and I don't know. It's 2,000, 1,000. Like what? It's busy when I do an animation, but I don't know. So there's this gap here that's the level of granularity. We're basically running processes in Linux, but wrapping them and giving them resource specs at a very granular level, and that's kind of unprecedented, right? Like that's you didn't do that in VMware, you don't do that in a lot of other platforms, but now we are wrapping request and limits around an Istio proxy. It's a very small thing, and it's hard to get that right. And I did this exercise where if I intuitively added up what I think all my Office apps need on my laptop, it would need 18 laptops, or I forget what the number was, 10 laptops, because I'm going to overestimate every one of them. But they all happily run together when I'm running my laptop. But if I have to give them requests, then all of a sudden I've made a problem for myself. So that's kind of what Kubernetes does, and it just requires some sophistication to come up with those numbers. They are very important, as you pointed out. They're just hard.
Very hard to get right. I see a few more questions. I think some of I can answer this time. So there is someone talking about requests, and there is something else in Kubernetes called quality of service, burstable, guaranteed, and best effort.
Mhm.
So I think these two things are not the same. So when we talk about requests, so we're basically saying that those resources are guaranteed by the kernel. So the kernel will basically just set the CPU groups, and will basically this amount of memory, this amount of CPU will be reserved. Whereas quality of service, burstable, or all the others are basically things that are assigned to at the pod level, and are basically designed to say, when the scheduler needs to evict pods, then it's going to look at this quality of service and the preemption to decide when these pods are going to be evicted. So if I set the limits equal to the request, they will basically assign a quality of service as guaranteed. So this is very unlikely that it's going to be evicted from my node. So the two things are not the same. Actually, they look at different layers in the stack. When we talk about guaranteed in request, we are talking a very low level. Those are resources like CPU and memory, which are provided to the processes. When we talk about quality of service in Kubernetes, we look at a very high level at the pod level, and we're basically deciding how these pods are going to be evicted in the case that we're running out of memory or something else. So this is perhaps where the confusion is coming from. There are several more questions on burst of traffic or CPU and memory limit. And I think I'm just trying to to understand. So I think, Andrew, one question is what is your suggestion when it comes to spikes in traffic, and there is not a limit on CPU? Of course, there's going to be a limit on memory. Can you readjust this memory and CPU allocation? Should you use HPA or VPA?
So and again, just to revisit some basics. So you said this in your content that setting CPU limits, we recommend not setting CPU limits. We've seen customers get away from that for the very reasons you mentioned. We don't really see CPU being a bit of a problem. For memory, we want to limit, but you want to have it nice and out of the way. Like, you don't want to have a limit so low that you're just going to accidentally hit it and get killed. So the purpose of the memory limit, as you pointed out, is just to make sure it doesn't run away and consume a node. And then even then, when that happens, it depends on the quality of service, because the things that are the most over their request are the ones that will get killed. So it might not even be the one that gets killed, the ones with no request. So it's a very complex area. So in a burst, like what we're a believer in is that get the limit again for CPU just out of the way, and or at least make sure they're high enough to account for any bursts you've seen. So when those patterns I showed in the demo are looking back through history, saying we've never seen it go above this level. So we're going to put the limit even higher than that, the high watermark we saw, just to make sure we're safe. So that, and the policy lets you say how far above that limit. So that's kind of your headroom before you really hit any limit. So we recommend just having a value that's way up out of the way, but enough to protect the nodes if something goes really wrong. And from a CPU perspective, again, we find no limits works best. You'll just get throttled if you use the entire node up, which is extremely rare. Like, again, I didn't have time to show the node level stuff, but most nodes are not very high utilization for CPU. There's lots of space to burst for CPU for spikes. I hope that answers the question.
Yeah, I think the takeaway, at least for me, is that sometimes you need to have requests higher than the average. What do you think is going to be the utilization? That's usually for spiky traffic and loads, but you should still monitor that sort of spikes to understand that if it's cheap CPU, you can still contend that CPU with the other processes if it is available. If it is memory, a little bit more complex, you will need to model that in such a way that if the spike goes up, then the application is not killed. So I think it's looking at basically two sides and finding a middle ground for CPU and sort of meeting the memory to whatever the limit is. I think that's the takeaway for me.
And one of the things we do, just to double down on that for a second, is that we analyze all the nodes. Again, I didn't have time to go down into it, and look at whether there's any saturation or imbalances for CPU and memory at the node level. And that's very important, because if you have saturation, like you're running out of memory out of CPU, that heavily dictates what you do in terms of, obviously, you're not going to have any room to burst if something is burstable. So a lot of all the recommendations are contextualized based on that, saying these ones should be done because that node is out of CPU, or it isn't out of CPU, or it's wildly out of balance. And so that's really the goal, I think, is at the node level, you want to make sure you have the headroom to meet all the workloads and be efficient and have good performance. And So the requests and limits, especially the request tuning, is to achieve that goal. To say, I want to make sure my systems are well utilized and that spikes they're not overutilized. And that's really the kind of the feedback loop that is Nirvana, where everything's well utilized. And it doesn't matter what the workload is, you're requesting the right amount for it so the system works well, if that makes sense.
Yeah.
Yeah.
And we discussed all of these actually recently in Andrew's podcast, which I think it will be live soon. And so if you enjoyed the talk today, I think there is a lot more than Andrew and I covered in the podcast. So as soon as this is live, I will share it as well. Andrew, I think I'm running out of time. I really enjoyed, as usual, really enjoyed the talk and the experience and everything you share with us today. Thank you very much for joining me.
My pleasure.
Thank you for you from home joining us today for the stream. I hope you enjoyed the session. If you've got more questions, please let me know. I will answer them. There are a few questions I didn't answer. I'm sorry. I will do in the comments. We will definitely share the links. We will share the links to the recording as well. Yeah, that's it. Thank you very much for joining. I hope you enjoyed.
Thanks.
Thank you. Bye.